All right, today we're diving into one of the biggest and yet faintest mysteries in the entire cosmos. We are going ghost hunting, looking for a magnetic ghost that seems to haunt the entire universe, a secret that's been hiding in plain sight since, well, basically the dawn of time. So here is the central puzzle, the big question. We totally expect to see magnetic fields inside of galaxies. I mean, you've got stars, black holes, they're messy, powerful engines. But what scientists have found, and this is the weird part, is that even the huge, almost perfectly empty space between galaxies is magnetized. How is that even possible? Where did this universe-spanning magnetic field come from? To really get to the bottom of this, we first need to zoom way out and take a look at the biggest thing there is, the universe's large-scale structure, something astronomers call the cosmic web. Okay, so try to imagine the universe not as just a random sprinkle of galaxies, but as this massive, interconnected structure, this cosmic web. Galaxies tend to clump together along these unbelievably long filaments of gas, and these filaments surround these vast, empty areas we call cosmic voids. And it's right there, in those filaments and voids, miles from any galaxy, that this strange magnetism lives. So what's the leading idea here? Well, the hypothesis is that this magnetism is ancient. It's a ghost, a relic, a faint echo left over from the very first moments of creation. Scientists have a name for them, Primordial Magnetic Fields, or PMFs. They might have been forged during cosmic inflation, maybe even before the Big Bang, or during some kind of wild phase transition in the baby universe. It's an incredible idea, right? But how on earth could you possibly test it? Well, the answer, it turns out, lies in using the universe itself as a giant laboratory. And to do that, you need to know how to read a very specific and very faint cosmic barcode. This is where things get really clever. To see what's happening in these empty spaces, we use light from quasars. These are super bright, super distant objects. As that light travels for billions of years to get to us, it passes through all the hydrogen gas floating around in the cosmic web. And that gas absorbs tiny bits of the light at very specific frequencies. What we see is a pattern of dark lines in the light spectrum, a unique barcode. We call this the Lyman-α forest, and it gives us an incredibly detailed map of the cosmic web. And here is where the plot thickens. Our standard model of cosmology, you might have heard of it, it's called lambda CDM, it makes a very specific prediction for what this cosmic barcode should look like. But when we actually look at the data from the Lyman-α forest, it doesn't quite match up. The real universe seems to have a bit of what scientists call extra power. All that means is that the gas is a little bit clumpier, a little more structured on small scales than our best model can explain. Could this be the fingerprint of that ancient magnetic ghost? To find out, an international team of researchers set out on a truly epic computational journey. They decided to build entire universes inside a supercomputer. And I want you to appreciate the scale here. They didn't just run 1 or 2 simulations. To hunt for the right answer, they ran over 250,000 different models of the universe. This is one of the largest simulation projects ever created to tackle a problem like this. The project was called Sherwood Relics, and you can think of it as a grand cosmic experiment. They created universes using just our standard physics, and then they created identical universes with one key difference, a faint primordial magnetic field. Then they tweaked all the other variables you can think of, heat, light, you name it, to ask one simple question. Which one of these simulated universes looks the most like the real one we live in? And after comparing all of those simulations to the actual data from the sky, they found their answer. And it was pretty remarkable. So here's the bottom line. The model that included those primordial magnetic fields, it was a significantly better fit for the real data. The starter model did an okay job, sure, but when you add that faint magnetic ghost into the simulation, the cosmic barcode it spits out looks a whole lot more like the one we actually see in the sky. And look, this wasn't just a tiny improvement. In statistical terms, it was a massive leap. Just by adding one new ingredient, this primordial magnetic field, the model became dramatically more accurate. This is a really powerful hint that these fields aren't just some abstract theory, but a real physical part of our universe. The study also let them put the tightest ever limits on just how strong this field could be. They found that any primordial magnetic field has to be weaker than 0.3 nano-Gauss. Now, that number probably doesn't mean a whole lot on its own, so let's put it in perspective. And this just says it all. This ancient magnetic field, the one that stretches across the entire cosmos, is billions of times weaker than the little magnet holding a shopping list to your refrigerator. It is almost unimaginably faint, and yet its influence is written all over the structure of the universe. So you might be thinking, okay, why should I care about a field that's so incredibly weak I could never, ever feel it? Well, because even though it's faint, its cosmic consequences are absolutely enormous. You see, this tiny magnetic field acted like a cosmic sculptor. It would have subtly increased the density of gas in the early cosmic web, which helped gravity pull matter together just a little bit faster. What does that mean? It means the very first stars and galaxies would have formed earlier than we thought. And that has huge implications for what telescopes like the James Webb are seeing in the early universe, and it helps us fine-tune our models of really fundamental physics, like cosmic inflation. And here's what makes this result such a landmark. This new limit on the field's strength is 3 times tighter, 3 times more precise than what we could figure out from the cosmic microwave background, which is, the most famous echo of the Big Bang itself. Using the Lyman-α forest has basically opened a new, much more sensitive window into the primordial universe. The discovery of this faint magnetic ghost proves that even the emptiest parts of space are filled with clues about the universe's violent birth. It really just leaves us with this tantalizing question. As our telescopes get better and our simulations get more powerful, what other ancient secrets, hiding in the faintest whispers of light, are we about to uncover next?